Welcome to lecture B14. In this lecture we will discuss the binomial, Poisson, and hypergeometric distributions. These are the three most important discrete distributions. Let's start with the binomial distribution. Suppose we shoot at a target and that the probability P of hitting the target is 2/3. Let x be the random variable representing the number of hits. If we shoot 3 times, what is little f of x? Okay, so remember that little f of x is for a discrete random variable, and capital X here is indeed a discrete random variable, because if we shoot 3 times and x represents the number of hits, then x can only have 4 discrete values: 0, 1, 2, and 3. And little f of x, recall that for a discrete random variable, little f of x is the probability that the random variable, capital X, has a particular value, little x. So what we want to do is, for each of the possible values, 0, 1, 2, and 3, we want to calculate what little f is. So let's start with little f of 0. What is the probability that we have 0 hits? Well, the probability of 0 hits means that we miss each time. And if the probability of hitting the target is 2/3, then the probability of missing the target is 1/3. And if we're going to miss with each of our 3 shots, then we have 1/3 times 1/3 times 1/3. And of course that's 1/27th. But for right now, I'm just going to write this as 1/3 to the 3 power. Actually, I tell you what, I think, no, I'll leave this as it is. I'll leave it as it is. Actually, I'm going to make a small change here, because you'll see why in a moment. Rather than saying that the probability of hitting the target is 2/3, I'm going to say it's 2/5. So if the probability of hitting the target is 2/5, then the probability of missing it is 3/5, and so this should be then. Actually, I'm going to change it still again. I'm going to make that 3/5. So if the probability of hitting, sorry about this, but I think you'll see why I'm changing these numbers at the end of the problem. So if the probability of hitting the target is 3/5, then the probability of missing the target is 2/5. And the probability of missing it all 3 times would be 2/5 times 2/5 times 2/5, or in other words, 2/5 to the 3rd power. Now, what about little f of 1? I encourage you, actually, I hope that you can find out all the rest of the values of little f, and I strongly encourage you to try to do that, to stop the video, try to do it on your own, and then come back. Okay, so let's see what you came up with here. Now, the probability of hitting it once, well, there are different ways in which we could hit the target exactly once. We could have, that's the probability. One way we could have it is hit, miss, miss, or we could also have miss, hit, miss, or we could have miss, miss, hit. All three of those ways would give us exactly one hit. So we have to add up the probabilities for all three of them. And notice that for each one, for instance, hit, miss, miss, okay? Hit, the probability is 3/5, and then miss and miss would be 2/5 and 2/5. On the other hand, the probability of miss, hit, miss would be 2/5 times 3/5 times 2/5. And then finally, the probability of miss, miss, hit would be 2/5 times 2/5 times 3/5. So you see that all three of those probabilities are the same, and I'll end up writing this as 3 times 3/5 to the first power times 2/5 to the second power. Now, what about the probability of 2 hits? Well, one way in which we could get 2 hits would be miss, hit, hit. Another one would be hit, miss, hit. And another one would be hit, hit, miss. Those would be the three ways, all the ways in which we could get exactly 2 hits. And for miss, hit, hit, we would have 2/5 times 3/5 times 3/5. For hit, miss, hit, we would have 3/5 times 2/5 times 3/5. And finally, for hit, hit, miss, we would have 3/5 times 3/5 times 2/5. Just as in our previous calculation, all three of these probabilities are the same, and so we can write this as 3 times 3/5 to the second power times 2/5 to the first power. And then finally, for little f of 3, well, that means that we have 3 hits, and the probability of each hit is 3/5, so the probability of all 3 hits is 3/5 times 3/5 times 3/5, or in other words, 3/5 to the third power. Now, if you look at this very carefully, you'll notice that an interesting thing is going on. If we go to f of 0, I mean, we look at f of 1 and f of 2 and see how similar those two formulas are, and notice actually that the first calculation, f of 0 and f of 3, could be made to fit into that pattern as well. We could write this as 1 times 3/5 to the 0 power times 2/5 to the third power. And we could write this last one as 1 times 3/5 to the third power times 2/5 to the 0 power. Now look, notice how this pattern is going. For the moment, we won't worry about the leading coefficient of 1, 3, 3, 1. We won't worry about that for the moment. But look at the rest of it. We have 3/5 to the 0 times 2/5 to the third, 3/5 to the 1 times 2/5 to the second, 3/5 to the second times 2/5 to the 1, and then 3/5 to the third times 2/5 to the 0. You see that the pattern that is developing there seems to be the following. We have f of n is going to be something. Again, now we're going to have to figure out this coefficient in the front, but the rest of it is going to be 3/5 to the n times 2/5. Excuse me. Let's say, yeah, well, this is fine. Times, actually, I think I want to change that. Let's change this to j. And so we'll have 3/5 to the j times 2/5 to the 3 minus j. And notice that that would give us the correct power for the 3/5 and 2/5 terms for each one of these. But now, what about this coefficient out front? Well, if you will recall from an earlier lecture we had, remember that this symbol, 3 over j, is read as 3 choose j, and it's equal to the number of ways to choose without replacement three objects out, j objects out of 3 objects. And the formula for it is 3 factorial over j factorial times 3 minus j factorial. And if you will calculate 3 choose 0, okay, that would be 3 factorial over 0 factorial. Now 0 factorial is defined to be equal to 1. So 3 factorial over 1 times 3 factorial, so that's 1. 3 choose 1 would be 3 factorial Okay, sorry for that interruption. So we have 3 choose 1 is equal to 3 factorial over 1 factorial times 3 minus 1. So that's 2 factorial. And notice that that's the same thing as 3 times 2 times 1 over 1 times 2 times 1. And so that's 3. And 3 choose 2 is 3 factorial over 2 factorial times 1 factorial. And you can notice very quickly by comparing this expression to that one that it's exactly the same. The denominator terms are just written in the reverse order. So this is also 3. And then finally 3 choose 3 is equal to 3 factorial over 3 factorial times 0 factorial, and that, since 0 factorial again is equal to 1, then 3 factorial over 3 factorial times 1 is 3 factorial over 3 factorial, which is 1. And so you see that the coefficients, if we use this formula, the coefficients will work out exactly correctly. 1, 3, 3, 1, just as they did up here. 1, 3, 3, 1. And so here is the formula. Here's a compact way of writing the formula. And remember now that j is the number of hits. So we have 0 is, well, we want to make this very clear. J equals 0, 1, 2, or 3. And there is your formula for the probability function. And this formula is actually an example of the formula for the probability function for a binomial distribution. The idea here is that we have n shots. In this case, n was equal to 3. The probability of hitting is p, and the probability of not hitting is 1 minus p. And so let's summarize it like this. If we have n trials, or we'll say n shots, and the probability of hitting is p, then the probability of J hits is okay. Again, if we have n shots and the probability of hitting on each shot is p, then the probability of J hits is p to the j times 1 minus p to the n minus j. Now this much I think makes sense to you probably, because for each one of our hits, each one of the j hits, the probability is p. So that's how we get p to the jth power. And then if we're hitting on j shots out of a total of n shots, then that must mean that we're missing on n minus j shots. And the probability of a miss, since the probability of a hit is p, the probability of a miss is 1 minus p. So we have 1 minus p, which is the probability of each miss, times n minus j, which is the number of misses. But now we have to account for that term out in front, which will be n choose j. Now, where does that come from? Well, think about it this way. Okay, we're looking for the probability of hitting j times out of a total of n shots. Well, let's just to make this a little more definite, let's think of maybe n is 100. We take 100 shots, and maybe j is 27. So we want to know the probability of hitting 27 times out of 100. Now we'll have then the p to the 27th times 1 minus p to the 73rd power. But what is this n choose j, which in this case will be 100 choose j? What does that represent? Well, there are many different ways in which we could hit 27 times out of 100. We could hit on shot number 1, shot number 2, all the way up to shot number 27, and then miss the next 73. Or we could hit on shots number 1 through 26, and then miss on 27, and hit on 28. Or, and you get the idea right away. We could hit on shots 1 through 25, and then miss on 26, and hit on 27 and 28. There's just a very large number of ways to choose which 27 of those shots, which of 27 of the 100 shots we hit on. And what is that large number equal to? It's n choose j. It's the way of choosing the j shots on which you'll hit out of the n total number of shots. So this right here is the binomial formula, binomial distribution. This is the probability of j. And here it's understood that j is, this formula is good for j equals 0, 1, 2, all the way up to n. And so there is the binomial formula for you that is appropriate for binomial distribution. Of course, if you would like to stick with the notation that is a little more similar to what we've been doing, instead of j, if you wanted x, then this would become f of little x is equal to n choose x times p to the x 1 minus p to the n minus x. X is equal to 0, 1, 2, dot, 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 n. And now at this point, before going any further, I'd like to make a comment. In the back of your book, in one of the appendices, there are, in fact, it's Appendix 5 at the back of your book, and this is important now. There are 4 tables. Table A5, which is for the binomial distribution that we've been discussing, and table A6 for the Poisson distribution, which we're about to discuss. And then also there's tables A7 and A8, both of which pertain to the normal distribution. Now, we'll be discussing the normal distribution in our next lecture, but all of these tables are important for you in solving some of the problems that we'll be doing. Now, certainly, I don't think, if you notice all the entries in these tables, they're to 4 decimal places, and I don't think it's necessary for you to memorize all of that. I believe if you'll just memorize these tables to 3 decimal places, all these numbers, for instance, like for right here, there's a 0 point at the top of this column, so that means that this number here is supposed to be 0.0486. So you can just memorize for that one 0.049. So if you'll just memorize the numbers in these 4 tables, but only to 3 decimal places, then you'll be in good shape to solve the problems that we'll be doing. And now notice for the binomial distribution, just to show you how this all fits together here, remember again, the binomial distribution looks like this. F of x equals n choose x, p to the x, 1 minus p to the n minus x. And so here you have a table of values of the binomial distribution for various values of p, and for various values of n and various values of x. And actually you have little f of x and capital F of x. Remember, little f of x is the probability function, and capital F of x is the distribution function or cumulative distribution function. Now, for the binomial distribution, that formula is actually pretty easily calculated using a calculator, but so this table you might not refer to as much, but some of the other tables will be more useful to you. So we will be referring to those in future problems. Okay, so now let's go back to lecture 14, and now that we've discussed the binomial distribution, let's next look at an example of the Poisson distribution. Okay, a good example of the Poisson distribution that is also gives us more insight into the binomial distribution is problem 24.7.6. And this problem says the following. Suppose that 4% of steel rods made by a machine are defective. The defectives occurring at random during production. If the rods are packaged 100 per box, what is the Poisson approximation of the probability? Actually, I'm going to change the wording here a little bit. Well, maybe I'll just put it like this. What is, and then I'm going to put in parentheses, the Poisson approximation of, and then I'll close the parentheses and say the probability that a given box will contain zero, 1, ... 5 defectives. Okay. Now, what I'd like for you to do in considering this problem is to first ignore these words that are in the parentheses. So just think that this that the question is, if the rods are packaged 100 per box, what is the probability that a given box will contain 0, 1, ... up to 5 defectives? And we're told again that 4% of steel rods made by a machine are defective. Well, if you didn't have those words, so without the words in parentheses, we're going to solve the problem that way first, and then we're going to come back and solve it with the words in parentheses. Now, I hope that you will see that if we don't have those words in parentheses, that's how we're going to try to tackle this at first. If we didn't have those words present, then this would be a good example of where we might use the binomial distribution. Because for any given rod, there's two possibilities. There's the possibility that it is defective, and the probability of that is 4%, or the probability that it's not defective, which is 1 minus 4%, or 96%. And so we want the probability of 0, or 1, or 2, or 3, all the way up to 5 defectives. And so what do we get? Well, we can summarize this very quickly in the following way. We'll say, without the words in parentheses, so in this case, we would use the binomial formula, and so we would have f of x is equal to, now n in this case is 100, so 100 choose x, that is choosing out of the 100 steel rods in a box, which X of those will be defective. And then we will have P, which is 0.04 to the X power times 0.96, that's 1 minus P, to the 100 minus X power. And there's the formula, and that's actually good for all values of X, not just 0 up to 5, but 0 up to 100. And that solves the problem just that easily if we did not have the words in parentheses. The only problem there at all is, notice that we do have to calculate some very large numbers. We have 100 factorial in the top here, and depending on what X is, we will have perhaps some large factorials in the denominator of this expression as well. And furthermore, another numerical difficulty that we could have here is we have a rather small number here being raised to perhaps a rather large value. So in other words, X could go all the way up to 100, and let's say that X were equal to maybe 93. 0.04 raised to the 93 power would be quite a small number, and if you were doing this on a handheld calculator, you might run into some error depending on the number of decimal places that the calculator actually retained in calculation. So that's the only difficulty. But this value right here is exactly correct. But because of those numerical difficulties that we just mentioned, we do have as well the Poisson approximation, and let's learn about that a little bit. In the limit as P goes to 0 and n goes to infinity. So in that limit, as we go to a large number of trials and a small probability, and where NP approaches a finite value, the binomial distribution will become identical to the Poisson distribution. And the Poisson distribution is given by little f. The probability function for the Poisson distribution is given by little f of x is equal to mu to the x power over x factorial times e to the minus mu power, where x can be 0, 1, 2, ... We don't put an upper limit on here because remember we're thinking of n as approaching infinity. Now, what is mu? Well, mu is the average, is the mean value that you would obtain, and of course, if 4% of steel rods are defective, and we have 100 per box, then the average number of defectives per box would be 4% of 100, or 4. So in this case, f of x would be equal to 4 to the x over x factorial times e to the minus 4. And that formula is good for positive integer values of x. And that is the answer for this problem when we're using the Poisson approximation. And let's just compare these two for comparison of the results obtained using both formulas. Okay, so we will calculate f of x, and I'll say binomial, and f of x Poisson, and then in this column we'll have x 0, 1, 2, 3. I think that will be enough. I won't go all the way up to 5. But let's calculate these two formulas. Calculate f of x in both of these ways for these values of x, and see just how closely the Poisson approximation does approximate the binomial in this case. Okay, now to fill in this table, the first thing I want to point out to you, remember we have the tables for the binomial and Poisson distribution. Now, in case you have not yet had a chance to memorize those, for the binomial distribution, here's our table, and we see that unfortunately this is not going to help us in making the calculation that we want to make for this problem. And the reason is that in this case, here's our binomial formula, and in this case we have n is equal to 100, but if you look at the table here, the table for the binomial distribution, we're only going up to n equals 8. So to calculate the formulas here in this table for the binomial, we're going to have to just go ahead and plug into this formula and calculate them. And when you do that, the values that you will get are 0.0169, 0.0703, 0.1450, and 0.1973. And I encourage you to try to calculate those for yourself and make sure that you understand how to handle these factorials that appear in this first term, and to get those values. Now, for the Poisson distribution, the situation is a little different. Now, here's the formula, and actually this is quite an easy formula for us to evaluate using the calculator anyway. But in this case, we can use the table, and it is important for you to understand how to use the table. And so let's make sure we understand that. So let's go back to the table, And here is the Poisson table. It's table A6. Now, mu, let's first of all think about mu. Remember, we said that there's 4% of the products are defective, and they come to 100 a box. So if 4% are defective and they come to 100 per box, the average number of defectives per box would be 4. So mu is equal to 4. So we're going to look on the table here, and we're going to come down to the mu equals 4 case, which is right here in this segment of the table. Mu is equal to 4. And notice that they have two columns here, one for little f of x and one for capital F of x, and we're calculating little f of x. And again, we have 0 point at the top of the column, and that's understood to mean that every one of these numbers will be preceded by 0 point. And then we have x over here, so we have 0, 1, 2, and 3, which is exactly what we want. And so the values we're getting are 0.0183, 0.0183, and the next one will be 0.0733, 0.0733, and the next one will be 0.1465, 0.1465, and then finally going back down to the Poisson, I accidentally closed that. Okay, so here we are at mu equals 4 again, and the next one is 0.1954. 0.1954. .1954. And you can see now by comparing the values in these two columns that indeed the Poisson distribution in this case seems to be a very good approximation to the binomial distribution. And again, that's going to be the case when p is quite small and n is quite large. And so there you have it. That's how we would do this problem. And in fact, we've looked at this problem in two different ways. One was using the binomial, you're treating it as a binomial distribution, and the other one treating it as a Poisson distribution. So that's an example of how we would do that. And now the final problem that we want to consider for this lecture is an example of the hypergeometric distribution. And the example that we will turn to in this case is actually from a different section. It will be problem 24.4.12. And this one says if 3 suspects who committed a burglary and 6 innocent persons are lined up what is the probability that a witness who has no knowledge and who is forced to pick, I guess actually a witness who has no knowledge is not really a witness, but anyway, actually the wording of the problem says a witness who is not sure, but we technically we really want a witness who has no knowledge whatsoever, so that he's choosing at random, completely at random. So anyway, so it says, what is the probability that a witness who has no knowledge and who is forced to pick 3 persons will pick the 3 suspects by chance, or 3 innocent persons by chance. Now, this is actually sort of a tricky problem, and I strongly encourage you to stop the video now, give this some thought, try to work it on your own, and then come back and we'll do this together. Okay, so for this problem, I want to do it a little bit more generally than what the problem is asking. Let's let x be the random variable that represents the number of suspects chosen. The witness is choosing 3 people, and there are 3 suspects and 6 innocent people, and so x represents out of those 3 that the witness chooses, x represents the number that are suspects. And since there are exactly 3 suspects in the lineup, and the witness is choosing 3 people, then the possible values are 0, 1, 2, or 3. Now, I think you can actually, the two problems, or the 2 questions that are asked in this problem, these 2 questions can be answered fairly easily. Let's try that at first. So, the first question is, what is the probability of picking all 3 suspects? So that's probability that x is equal to 3. And I think that you can probably solve this one pretty easily. If on the first choice, when the witness makes his first choice, okay, since there are 3 suspects and there are 9 total people, the probability that he picks a suspect on the first choice is 3 out of 9. And then the probability, since he's not going to pick that person again, you can think of this as picking without replacement. So he's going to pick that first person, they're going to put that person to the side, and now the probability that he will pick another suspect, since there are 2 suspects left out of a total of 8 people, the probability would be 2 out of 8. And then the probability that with his third pick he would get the third suspect, since there's only 1 suspect left out of 7 people, that would be 1 out of 7. And so the probability that he gets all 3 suspects is going to be 6 divided by 9 times 8 times 7. And that would be little f of 3. So that one is pretty straightforward to calculate. And likewise, the probability that he gets no suspects at all, in other words, that he gets all innocent people, I think that one is pretty easy to calculate. Okay, let's do that. The probability that he gets an innocent person with his first choice is 6 out of 9. And the probability then that he gets an innocent person on the second choice as well would be 5 out of 8. And the probability of an innocent person on the last choice would be 4 out of 8. 4 out of 7. And so in this case, we'd get 120 over 9 times 8 times 7. So the two questions asked in this problem are pretty straightforward. But what if we wanted to know the probability of getting one suspect or two suspects? Now, I think you can probably figure those out, but in fact, let's go ahead and do that with the knowledge we already have, but then we'll see how it fits in with a hypergeometric distribution. So let's calculate the probability of getting one suspect. Well, you can see right away there's a little bit of difficulty here, because on what pick will he get the one suspect? Will he get the suspect on the first pick, or the second pick, or the third pick? And so we're going to have to calculate all three of those probabilities together. And likewise, if we wanted to know the probability of getting two suspects, again, would it be the first two choices, or the first choice and the third choice, or the second choice and the third choice? You have multiple cases to consider, and that's the reason that we have the hypergeometric distribution for this problem, is that it will give us everything at once. But let's go ahead and do it in the familiar way now, and then we'll come back and show how we could do it all at once with a hypergeometric distribution. So again, to get one suspect, we would have suspect, innocent, innocent, plus, that would be one way we could get one suspect, or we could have innocent, suspect, innocent, or we could have innocent, innocent, suspect. And let's calculate those three probabilities. So the probability of suspect, innocent, innocent, okay, the probability that the first one is suspect, as we've already said, is 3 out of 9. And then the prospect that the next one would be would be innocent. Okay, there's 6 innocent people out of 8 remaining, so we would have 6 times 8. And then the next one would also be innocent, would be 5 out of 7. Now the probability of innocent, suspect, innocent. Okay, the first one would be 6 out of 9, and then 3 out of 8, and then 5 out of 7. And then finally, the probability of innocent suspect would be 6 out of 9 times 5 out of 8 times 3 out of 7. And notice that all three of those probabilities are really the same. In all three, we have 9 times 8 times 7 in the bottom, and 6 times 5 times 3 in the top, but the 6, 5, and 3 are just in different orders. So we have 3 times 6 times 5 times 3 over 9 times 8 times 7. And now finally, I hope that you can do f of 2. If you haven't already done this, try to do f of 2 on your own, and then we'll see how to solve this problem with the hypergeometric distribution. So f of 2 would be probability of innocent, suspect, suspect, plus the probability of suspect, innocent, suspect, plus the probability of suspect, suspect, innocent. And, okay, the probability of the first one is innocent is 6/9, and then the next one would be suspect, would be 3 over 8, and the next one would be suspect, would be 2 over 7. And then for the next case, the probability of the first one is suspect is 3 over 9, and then 6 over 8, and then 2 over 7. And then finally, the probability of suspect innocent is 3 out of 9, 2 out of 8, and 6 out of 7. And all three of these probabilities are the same. We always have 9 times 8 times 7 in the denominator, and 6 times 3 times 2 in the top. So we get 3 times 6 times 3 times 2 over 9 times 8 times 7. And now we have calculated the probability function for x. Here's f of 0, f of 1, f of 2, and f of 3. So we've calculated that probability function for all the possible values that the random variable can assume. And of course, if you add up all of these numbers, they should be equal to 1, because that's all the probabilities. Those are all of the possible values that x can assume. But now let's see how to do this with the geometric distribution. And, you know, this is similar. What we've just done right here is similar to what we did at the beginning of the lecture. We looked at a problem and we calculated the different probabilities using methods we already knew, f of 0, 1, 2, and 3. But then we compared that to the binomial formula, which could calculate f for all possible values at once. And it's going to be the same thing here. In this problem, we've used methods that we've already learned about to calculate all these separate values of f, and now we will use the I'm sorry, I said geometric, but this should be hypergeometric. Now we'll be able to calculate all these at once with a hypergeometric distribution, and the way it goes is this. Okay, the probability, if there are 3 suspects altogether, and we're going to choose 3 of those suspects, then the probability that we will get x of the suspects is the following. First of all, we have a total of 9 suspects. And so I'm going to put 9 in the bottom, and we're choosing 3 of those. So 9 choose 3 represents the total number of ways in which we could choose 3 people out of those 9 people. Okay? And now in the numerator, we want to know the number of ways in which, if we make a choice, we would get x of the suspects. Well, think about it this way. We're getting x of the suspects out of 3 suspects. So the number of ways to choose x of the suspects out of 3 is 3 choose x. And now if we're choosing, we're making 3 choices, and presumably now 3 of them, we're making 3 choices and x of them were suspects, so that means that 3 minus x were not suspects. So of the, or in other words, 3 minus x were innocent. So out of the 6 total innocent people, 3 minus x were, out of the 6 innocent people, 3 minus x of those were chosen. And this is the hypergeometric distribution. Now let's make sure, actually before we proceed, let me look up one thing here. So let me compare this to what is in your book to show you that this is the hypergeometric distribution. So what you have in the book is the following. It says f of little x is equal to capital M choose x over n minus m, or n minus x divided by n choose little n. And so you can see that the formula that we derived for this problem is exactly the hypergeometric formula, with little n equals 3, capital M is also equal to 3, capital N is equal to 9, and of course x is just equal to x. So what we have here is indeed exactly the hypergeometric distribution, and I won't check it for every single value that we calculated before, but just to make sure it works out correctly, why don't we check it for maybe x equals 1. So for x equals 1, let's see what this would give us. F of 1 would be 3 choose 1 over 6 choose 3 minus 1 is 2, divided by 9 choose 3. And let's see what that would give us. So we have 3 times 2 times 1 over 1 times 2 times 1. And then we have 6 factorial. I'm not going to write out everything there. I'll say 6 factorial. Actually, I'll write it 6 factorial. I'm going to write like this. I'm going to write it as 6 times 4 times 4 factorial. And then in the bottom, we'll have 2 factorial, which is 2 times 1, times 6 minus 2, or 4 factorial. And likewise, I'll pull a similar trick down here in the bottom. I'll write 9 factorial is 9 times 8 times 7 times 6 factorial. And then we'll have 3 factorial, which is 3 times 2 times 1, and then 6 factorial. And now you see that this 6 factorial and that 6 factorial will cancel, and this 4 factorial and this 4 factorial will cancel. And so let's see what we're left with. We have, let's see, 2 will cancel, 1 will cancel, and so we're in the top, we're left with 3 times, okay, and 6 times 5 is 30 divided by 2, so we have 15, 3 times 15 in the top, and in the bottom we have 9 times 8 times 7 divided by 6. And so I'm going to pull that 6 up to the top, and that'll give me 6 times 3 times 15 over 9 times 8 times 7. And before proceeding any further now, let's compare this to what we had up above. Okay, notice that for f of 1 up here above, when we were calculating it using our, let's say, previously learned techniques, we have a 9 times 8 times 7 on the bottom. That matches exactly what we have here, 9 times 8 times 7. And we have a 3 right here to match this 3. We have a 6 to match this 6. And then up here we have 5 times 3, and down here we have 15. So indeed, we are obtaining, using the hypergeometric formula, we are obtaining exactly the same value for f of little 1 as we did using our previously learned techniques. But the advantage of the hypergeometric formula here is that it has given us all of these, a formula that will calculate all of these in one compact form, rather than having to calculate each one of these separately. So that's how you, that's an example of the use of the hypergeometric distribution. So now let's look at some problems for this lecture. Problems for lecture B14. So for the problems for this lecture, problem B14-1, I suggest that you see problem 24.7.5 in the book. It's not exactly the same as this, but it's similar. This problem says that 5 fair coins are tossed simultaneously. What is the probability that the number of heads is less than or equal to 3? And I'll give you the hint that your table for the binomial distribution could be helpful here, but you don't have to use that. The choices are A, 0.96875, B, 0.84375, C, 0.8125, and D, 0.3125. And then problem B, 14-2, which is essentially identical to problem 24.7.14 in your textbook. It says if a ticket office can serve at most 4 customers per minute and the average number of customers is 120 per hour, use the Poisson distribution to find an approximate value for the probability that during a given minute customers will have to wait. And the choices are A, 0.0902, B, 0.0527, C, 0.0361, and D, 0.9473. And there will be another problem in class, and I'll go ahead and tell you in advance that, as you would probably figure, it's going to be on the hypergeometric distribution. So at a minimum, I would suggest that you write down that formula for the hypergeometric distribution and make sure you understand how to apply it, and then you'll see what the problem will be once you get to class. So good luck with these problems. And by the way, I hope you all did know that I was teasing about memorizing those tables. Of course, they will be given to you on the final exam. So that's it, and I'll see you Monday.